Welcome to the screencast on constructing Power diagrams. We will implement it in Python. My name is Manish Sharma and I'm supervised by Anna Hankin and Ifan Stephens. A Power diagram, also known as potential PS diagram, maps the thermodynamic stability regions of chemical species as a function of electrochemical potential and pH. It is widely used as an electrochemical stability map in various electrochemical applications, including electrodeposition, catalysis, and others. This is a typical example of Power diagrams for nickel water system, which we will learn how to construct in this screencast. To construct a Power diagram, we first need to calculate the speciation diagram. This means determining the activities of active species at the same oxidation state, which can be done by solving the mass balance and thermodynamic equilibrium equations. This is the speciation diagram for the nickel water system, assuming a total nickel concentration of 0.2 molar, an ionic product of 1 to the power negative 14. And here, nickel 2 plus and nickel hydroxide both have an oxidation state of +2 and they compete with each other. Nickel remains dominant in acidic condition while nickel hydroxide becomes dominant in the basic region. We can also calculate at what pH will activity of nickel 2 plus will be same as the activity of nickel hydroxide through analytically. So for the solubility equilibrium, this is the expression and we can determine this analytically for the pH at which their activities becomes equal. This speciation diagram is essential for constructing Power diagrams as the Nernst equation is only valid when the relevant species becomes dominant. We therefore need to determine the activities of nickel 2 plus and nickel hydroxide across the full pH range. Not all nickel added to the solution will dissolve as free ions. Some of it will precipitate. The amount that precipitate is governed by the solubility limit of nickel hydroxide. When the ionic product of the nickel and nickel hydroxide exceeds the solubility limit, precipitation occurs. Under acidic condition, the hydroxide concentration is very low. As a result, the calculated nickel activity can reach values as high as 10 to the power 10, which is not thermodynamically feasible and must therefore be constrained. There are two approaches to handle this. The first is to take the minimum of either the solubility limited nickel activity or the total concentration added to the solution. Since the dissolved activity cannot exceed either of these limits, the second approach is to use a capping function, a smooth mathematical alternative that limits the nickel activity to the total nickel concentration. We will implement both approaches in the code and analyze them further. Once the activity of dissolved nickel is known, we can determine the activity of nickel hydroxide. It is equal to the greater of either the difference between the total nickel concentration and the free dissolved nickel, or it will be zero. The latter one applying when no precipitation has occurred. With the speciation diagram established and the activities of nickel 2 plus and nickel hydroxide determined, we can now apply the Nernst equation. All the calculation in this tutorial assume a temperature of 298 degree Kelvin. The Nernst equation for any reduction reaction can be expressed as shown on the screen. Evaluating RT over F at 298 Kelvin and converting to the base 10 logarithm gives a prefactor of 0.0591 volt. Here m is the number of proton transferred and n is the number of electron transferred. For reactions involving no protons, m equals 0. For solid activity, the activity of solid phase would be 1. The simplified Nernst equation for the reduction of nickel 2 plus to solid nickel can be expressed as this one, as it is shown in the screen. Once we establish the Nernst equation for one species, we can similarly apply the same approach to all the relevant electrochemical reactions. Reactions that depend on nickel activity will reflect that dependence, and reactions involving protons will show a corresponding pH dependence. The hydrogen evolution reactions and oxygen evolution reactions are also included as they define the thermodynamic stability window of water and serve as important reference boundary in the Power diagram. This concludes the theoretical overview. With that foundation in place, let's move to the Python implementation. The first step is to get to a Python IDE. I'm using Google Colab and importing important libraries, NumPy for numerical computation and Matplotlib for plotting. Next, we define our constants. The total nickel concentration is set to 0.2 molar. The water dissociation constant, Kw, is 1 times 10 to the power negative 14, and the solubility product, Ksp, is 10 to the power negative 15.743. We also define a pH grid of 100 evenly spaced points ranging from pH 0 to 14. Next, we define a speciation function that takes the pH grid as input. Inside, we first calculate the hydroxide ion concentration from the ionic product of water, Kw, and pH. Then compute the saturation concentration of free nickel ions using the Ksp expression. As discussed in our theoretical overview, two methods are available to constrain the free nickel activity. Only one is active at a time, with the other commented out for later comparison. Finally, the function computes the nickel hydroxide concentration as the remainder of the total nickel not present as free ions, and return the activity of both species. We then define the Pauve function, which takes pH and the free nickel activity as inputs. To avoid numerical issues from 0 or negative concentration, the nickel activity is clipped to a minimum value of 10 to the power negative 30. The function then calculates the equilibrium potential boundaries for 6 nickel redox and precipitation reaction, each expressed as a function of pH and nickel activity using the Nernst equation. It also computes the oxygen evolution and hydrogen evolution reference lines. All 8 boundary lines are returned for plotting the Pauve diagram. We now call both functions over the full pH grid to obtain the speciation profile and Pauve boundary lines. We then determine the crossover pH, the point where the free nickel and nickel hydroxide concentrations are equal. This is done in two ways: numerically by finding the pH at which the absolute difference between the two species is minimized, and analytically using the exact expression derived from the Ksp and total nickel concentration. Both values are printed for comparison, serving as a quick validation check between the numerical and analytical approach. Initially, with a small number of grid points, we notice a slight difference between the two values. However, as we increase the grid resolution, the numerical solution converges closer to the analytical result. We now plot the speciation diagram showing the activity of free nickel ions and nickel hydroxide as a function of pH. We now add two vertical dashed lines, one in black marking the numerical crossover pH and one in red marking the analytical value. We now plot the full Pauve diagram showing all 6 nickel reaction boundary lines alongside the oxygen and hydrogen evolution reference lines, each leveled accordingly. We also add a vertical dash line in red marking the crossover pH obtained from the speciation analysis, linking the two diagrams together. We now determine which boundary line is dominant at each pH using the speciation diagram as a guide. We create two Boolean arrays, one identifying where free nickel ion dominates and another where nickel hydroxide dominates. Based on this, the lower boundary is assigned R1 where nickel ions dominate and R2 where nickel hydroxide dominates. Similarly, the middle upper boundary switches between R3 and R4 depending on the dominant species. R5 is applied across the full pH range as the uppermost boundary. We now plot the cleaned up Pauve diagrams, this time showing only the dominant boundary lines. The lower boundary switches between R1 and R2, the middle boundary between R3 and R4, and R5 runs across the full range as the uppermost boundary. The oxygen and hydrogen evolution lines are also included, along with the crossover pH marked as a vertical red dashed line. Compared to the earlier plot, this gives a much clearer picture of the relevant stability regions. Finally, we produce the complete field Pauve diagram. The metallic nickel region is filled from bottom up to the lower boundary line. The nickel hydroxide region is then filled between the lower and upper boundaries, but only where nickel hydroxide is the dominant species. This is followed by the free nickel ion region, filled between the same two boundaries, but where nickel ion dominate instead. Nickel oxyhydroxide is then filled between the upper and uppermost boundaries, and finally nickel dioxide is filled above the uppermost boundary up to the plot limit. Black boundary lines are added to clearly separate each
instability regions along with the oxygen and hydrogen evolution reference lines as black dashed line and the crossover pH marked in red. This gives the final Poiret diagram clearly showing the stability region of all nickel species as a function of both pH and potential. We now implement the second method, which uses a capping function to constrain the free nickel activity. Upon switching to this method, we observe that the numerical and analytical crossover pH values no longer agree, and notably, increasing the grid resolution does not resolve the discrepancy, suggesting that the difference is not a discretization error fact, but rather a fundamental consequence of how the capping function constrained the speciation. This difference also manifests visibly in the Poiret diagram. Switching back to method 1 restores the agreement between the numerical and analytical solutions, leading us to conclude that method 1 is better suited for this analysis. Thank you for watching. I will see you in next one.